Hello, and welcome to a digital mathematics lecture for Salt Lake Community College. In this video, we're going to be going through Module 10 for Math 1030, the normal distribution. Specifically in this video, I'm going to be going through two different sections of the normal distribution. First, I'll be talking about the properties of the normal distribution, which shouldn't take too long, and then we're going to go through some examples of applying the normal distribution and specifically what we call the empirical rule. In a second video, I'm going to be going through how to calculate what we'll call z-scores, which again I'll address in a little bit. For now, though, I just want to talk about what the normal distribution is and how it's applied. So the normal distribution is going to be this shape that we have represented here, this nice curvature shape that looks kind of like a bell, and sometimes we even call it a bell shape. We talk about this bell shape because there are a lot of distributions and data sets that we'll work with that come out to look like this data set. Maybe if I'm talking about how long a battery lasts, and on average it lasts 100 hours. Well, I'm going to have some batteries that last a little bit longer than that, some batteries that last a little bit less than that, because there's always a little bit of variance there. I could also consider a data set that's cholesterol level, or weights or heights of individuals. All of these will have a defined average, and then I'm going to have some individuals that are higher or lower than that defined average. And then if we were to plot that using what we talked about in chapter 8 and 9, a histogram, then we'll typically get a graph that looks something like this. A histogram that looks about like that. Not perfectly normal, or not perfectly bell-shaped and symmetric, but approximately so, where we have an average defined right here in the center, and then we have some data that varies above it and some data that varies below it. You'd be surprised how many data sets do create this approximate shape. And because there are so many data sets that create this approximate shape, we can use this. We can apply this shape that we see so often and calculate the area under that shape to find probabilities of something. Maybe if I wanted to find the area of these two bars and then or how many individuals are in each of those two bars and then put that out of the total, that would create a probability. Or similarly, I could do the same thing in this graph over here and find the area between these two values, and that would represent the probability of those values. The normal distribution shows up so much that we are going to use it to approximate a lot of data. However, in most instances, we're going to have to know that the distribution is normally distributed, or it creates an approximate bell shape. However, in all the situations that we'll have that given to us. If we were to continue in statistics, there are a lot of ways to verify this kind of situation. Okay, so that's kind of a quick rundown of what the normal distribution is, but now what I want to go through are some properties of this distribution itself. Okay, so the first property of a normal curve is that the normal curve has a single peak. So there is a single peak at the center of the graph. Hold on. There we go. There is a single peak at the center of the graph. As you can see represented here, there's that middle line in that normal distribution that represents the peak there. And that peak is also going to be represented as the mean. So this represents the mean, or the median, or the mode. Essentially, all three of those are equal at that center point, which is one way of trying to find if a situation is normal. So I'll say that as a side note. One way of determining normality, or trying to determine if the graph is normally distributed, is by checking if the mean is approximately equal to the median. That's one way of checking for normality there. There we go. So if the mean is 100 and the median is 99, that might be close enough to say, okay, the situation probably is normally distributed. However, we won't really need to check that too much. Just know that the center of this curve is represented by the mean itself, or mu, as we'll typically use. So we'll typically represent the center by the letter mu. Another thing about the normal distribution is that the area between any given x values, and we say x values because if you notice, we're going to be identifying values on the x-axis below the curve itself. So the area between any given x values will represent the probability of getting a value within that range. Which means it's really, really good for continuous data sets. Although it could be used for discrete data sets, we're going to typically use those as continuous. So all we're going to need to try to find in this curve is the area between any two given x values, which sounds easy on paper, but it's going to be a little bit complex. And there's a couple different ways of going about it, which we'll address in the following two sections here. All right, a couple other things. Values further away from the center, or the mean, are considered less common than those close to the center. Basically, the height of the curve really represents the probability of something. So if the curve is taller at some point, that means it should be more likely to get a value there. But if we're considering values that are further away from the center point, maybe it's higher up or lower down. So if I get a value up here, maybe this is 104 compared to a mean of 80. Well, that value seems rather unlikely compared to maybe a number like 87. That's far more likely because the curve is a lot taller at that point. So that's what I'm talking about there. Okay, let's see here. The area under the curve, so the entire area under the curve is equal to 1. We say that because, again, the area under the curve between any given points is supposed to represent probability. So the full curve should represent 1 or 100% of the data. The curve is considered symmetric. And what that means is 50% of the data is above the mean. And also 50% of the data is below the mean. So it's symmetric about that mean with mu. So any data above it or below it is equal to each other, and we are going to use that symmetry process a lot, so keep in mind that it is symmetric. The curve never touches the x-axis. And what that means is we consider that the graph, as you continue further and further and further up and up, this curve never actually touches the x-axis. That way, there's always some area above it, or some area way up here. So maybe between this value and this value, there is some positive area there. And that way, we can talk about the probability up there, even if that probability is incredibly unlikely. We always consider that there is area up there, which means technically that this graph spreads from negative infinity up to positive infinity. It's just the closer and closer you get to those infinities, or the further away you get from the mean, the less likely it is. The other reason we don't want it to ever touch the x-axis is that typically if it were to touch the x-axis, that usually implies that the curve then continues past it. For example, if I had a curve like this, that does touch the x-axis, that then implies that the curve continues past it in that direction. And then any area past that would be considered negative, which doesn't make sense for probability. Probability should never be negative. So we never want the curve to touch the x-axis. So That's kind of a small note. And lastly, but most importantly here, the spread of the data, or the normal distribution, is defined by the standard deviation. Which is really, really important for us. So I'll put a few stars there. That is really, really important for us because we've talked about the standard deviation, we've calculated the standard deviation, but when we did that, we kind of put a asterisk there saying, hold on this, it will be useful in a bit. This is where the standard deviation is going to be useful. The mean will define the center of the distribution, but the standard deviation will define how the data spreads away from that. The bigger the standard deviation, the further the data spreads. The smaller the standard deviation, the less the data spreads. So the standard deviation is going to be really important for us. The previous note saying that the curve never touches the x-axis implied that it went from negative infinity to positive infinity, so I can't use a spread like the range to try to represent that, because then the range would just be infinity, or it spreads infinitely, which isn't really useful for us. We want how does the data spread compared to the mean given the data that we have, and that's what the standard deviation will provide for us. So the standard deviation is going to be very useful for us here, so that's a good note to keep in mind. But other than that, those are basically the properties of the normal distribution to keep in mind. There are going to be a couple other things, but first I just want to do a quick example just to make sure you understand how the normal distribution works. So this example here, I have draw a picture of the following normal distributions with the same center. So I say that both of them are approximately normal. And the distribution with a mean of 100 and a standard deviation of 20, and then a distribution with a mean of 100 and a standard deviation of 5. Okay, I'm going to see if I could do these in two different colors. So this first one I'm going to do in black, so I'll put a little black scribble next to it so you know which one I'm talking about. So to do this, I'm going to make a nice normal curve. If you've never made these before, trust me, you'll get used to them the more and more you do it, so just get around to it. Obviously, my handwriting's not the best on here, but it's fine. So I make a nice bell shape. I try to make sure that the curve never touches the x-axis, or I try to imply that. And we're going to represent the center of this curve as 100. Both of these have that same mean here, so that center is going to be here at 100. And then with a standard deviation of 20, okay, that implies that it spreads roughly this far. So maybe it spreads up to 120, 140, etc., etc., etc. But if I were to draw on top of that a normal distribution with a standard deviation of 5 instead, so I'm going to represent that in this reddish color here. Maybe it's purplish. That still has the same mean of 100, so it's still represented at the same top point. However, it does not spread as far. It has a standard deviation of 5. And what that implies is that the deviation itself, or the curve itself, it's going to look something like this. It's still centered at the same point, but it does not spread as far. Notice that the black one does spread further, so it's kind of stretched out. It's kind of as if somebody were to grab the ends of the curve and were to pull them side to side. So if somebody were to like grab this end of the curve and were to stretch it out this way, and this end of the curve and were to stretch it out this way, that's what would happen if you were to increase the standard deviation. And then if you decrease the standard deviation, that means that you're kind of putting your hands on the side of the curve and you're squishing it in, which will cause the curve itself to become less wide and will also kind of stretch to the top. And that's because it's far more likely to get values closer to 100 with the curve that doesn't spread as far. So that's what these curves kind of look like. They will always make this bell-ish shape, but how far it spreads will be defined by the standard deviation itself. Okay, at this point it's kind of an arbitrary spread there, and where I put 120 and 140 seems kind of arbitrary for now, but we're going to talk about in just a second what is a way of representing these values by using that standard deviation. and that's where we get to what we call the empirical rule. The empirical rule will be our first application of the standard deviation itself. The empirical rule is something that we use as a rule of thumb, hence empirical rule, to try to find how much percent of the data is within a certain amount of standard deviations. So the empirical rule is also, there's a typo here, that should say 68. The empirical rule is sometimes also known as the 68, 95, 99.7 rule. And what that means is that if you go a certain amount of standard deviations away, then that will represent that percentage of data. So 68, 95, 99.7, those three numbers will represent the three different standard deviations. If you go one standard deviation away, that will represent 68% of the data. 2 will represent 95, and 3 will represent 99.7%. As dictated by the pictures here. I have in the center here the mean in every single instance, and then for the first one I went up 1 and down 1 standard deviation, so those two values represent 68% of the data. For the second graph we went up 2 standard deviations and down 2 standard deviations. That's what this x-axis is representing. And then for the third one we went down or up 3 and down 3 standard deviations. That is also represented by the following three statements. Approximately blank percent of the data is between mu minus sigma and mu plus sigma. So that means down 1 standard deviation and up 1 standard deviation. That's 68% of the data from the empirical rule. If you go down 2 standard deviations and up 2 standard deviations, that represents about 95%. And if you go down 3 and up 3, that represents almost 100%, but not 100. It represents 99.7% of the data. This is a very, very important rule of thumb. Not every single question will result in exactly a certain amount of standard deviations away, and we'll get to that in the second video. But we can use this as a rule of thumb to find approximately how much percent of the data. If you're also wondering where these values come from, because they seem kind of random and arbitrary, they're coming from processes that would be in calculus. In calculus, we talk a lot about how to find the area under a curve. And as we said, the normal distribution is a very common shape, and it has a defined formula itself. So there is a defined formula to represent this curved shape here. With that curved shape and what we call an integral in calculus, we can find the area under that curve. And so within 1 standard deviation represents 0.68 or 68%. So it's coming from calculus. Unfortunately, we don't have a lot of calculus here, so we can't really go into it too much more in depth. This empirical rule we're going to have a lot of questions with, so you can start to see the applications for. And in all of these questions, I'm going to have a small normal distribution printout so that we can work on it. I highly recommend when working through these or following along with the videos here, you do write down and draw the picture. It will always be important to draw the picture of the situation itself. It makes it so much easier to solve. When you can see the picture of what's happening, it makes it much, much better. All right, so the empirical rule, 68, 95, 99.7 for how many standard deviations away you're going from the mean. Notice that each of these are also down and up. So let's do a couple examples. And again, I'll write down up here just in case, 68, 95, 99.7. Those are very important numbers here. All right, for the second example, a random variable x has a mean of 160 and a standard deviation of 15. We want to answer the following. What is the probability that x is between 130 and 190? This question doesn't have much context to it because I just wanted to do a simple one with the bare bones information provided. However, we can still work through this. The mean is 160, and so on this curve, I'm going to represent 160 directly in the middle. And then what we want to find is the probability that x is between 130 and 190. Well, I want to see this via the empirical rule. So what I can do is start to draw or indicate the values via the standard deviation. So let's go down. If I go down 1 standard deviation, so if I go down 15, then I get to a value of 145. 160 minus 15 is 145. that's not quite the value I'm looking for, so I need to keep going. If I go down another standard deviation of 15, 145 minus 15 gives me 130. That's one of the values I'm looking for, so I can indicate that number here. Likewise, I can find 190 by going up standard deviations. If I go up 15, I get to 175, which is not quite 190, so I need to keep going. If I go up another 15, I get to 190. Therefore, what we're trying to find is the area between those two numbers. We're trying to find the probability that x is between 130 to 190. Well, 130 we indicated was 2 standard deviations down, so I'll say 2 sigma down. And then 190 was likewise 2 standard deviations up. So then, that means that via the empirical rule, 2 standard deviations is 95%. So we'd say the probability that x is between 130 and 190. That's how you would write it in probability speak or probability notation. However, don't always need to see this. That probability is approximately 95% via the empirical rule. Now this you don't need to write, this is more just for me to write, and so you can also see this notation. Sometimes some questions write this notation instead. But the answer was just looking for 95% here. So that's how we're going to apply the empirical rule. See how far the values in question are from the mean, and apply that to the empirical rule. Some are going to be incredibly straightforward, some are not. The rest of these examples that I have here, for example 2, are going to be some alterations of this basic concept. So for the second one, what is the probability that x is between 160 and 175? Well, 160 is the mean. We know that. That's still given to, in the basic example, these two values are always going to be the same. So the mean is still 160 and the standard deviation is still 15. And 160 being right in the middle, well, that means I already have one of the numbers indicated. I now need to indicate 175. And in the previous example, we noted that 175 was 1 standard deviation above the mean. Therefore, what we're trying to find is the area between 160 and 175. So this shaded region here. All right. Now, some may look at that and say, all right, well, 175 is 1 standard deviation away, so the answer is just going to be 68%. However, that is incorrect. The reason is because 68% represents 1 standard deviation in both directions. So if I were to go down another 15, down to 145, as we also indicated in the previous example, from 145 to 175 is 68%. And what we want is to find just this region, from 160 to 175. The savvy among you may have figured out what we're going to do, and what we're going to do is apply the fact that this is a symmetric graph. So we're going to apply symmetry to this. The way we're going to apply symmetry is that, well, if the area from 145 to 175 is 68%, and 160 is directly in the middle of that, that means I want half of this. The probability that I'm looking for, so the probability from 160 up to 175, this probability I'm looking for, I'm going to take 68%, and what I'm going to do is cut that in half, because I only want half of that region. Remember that because it is symmetric, that means that the area above and below is exactly the same. So if 145 to 175 is 68%, then that means 160 to 175 is equal to 160 to 145. So these should be equal. If I do 68 cut in half, I get an answer of 34%. Okay, so that's another example. All right, since I've scrolled down, I'm going to write again 68, 95, 99.7, just so you remember the numbers. What is the probability that x is less than 145? Well, yet again, I'll indicate the mean here in the center of 160. 145 is one standard deviation below that, as we've indicated in both of the previous examples. And what we want is a probability that x is less than 145, so that means we want this shaded region here. We want this tail. Well, how are we going to figure that out? 68, 95, 99.7, we're always talking about area between values, not above or below something. Well, we know that if we went one standard deviation away, as we talked about in the previous example, this shaded region here, which I'll color in a different color. Let's do this magenta-ish color. Okay. This region here, this represents 68% of the data. And we do also know something else. We know that the entire curve has an area of 1 or 100%. So this entire curve is 100%. Therefore, I can find the area of these two tails here, these two tails that I have shaded in black, by taking 68 away from 100%. So if I do 100% minus 68%, I get an answer of 32%. However, that is how much is in both of the tails combined, the left tail here and the right tail. Keep in mind, though, that we know symmetry. That means that this left tail is equal to the right tail. And since they're equal, that means I should be able to cut this in half, this 32%, to find how much is in each of them. 32% cut in half is 16%, meaning that this left tail here has 16%, this right tail here has 16%. That way 16, 68, and 16 all add up to 100%. So we have that the probability that x is less than 145 is about 16% via the empirical rule. All right, hopefully you're starting to see how the empirical rule is applied. It's essentially find the number that you're looking for in the description, so that 145, see how many standard deviations away that is, and then you can tell what numbers from the empirical rule you need to work with. If you notice, since 145 was just one standard deviation away, I didn't need to use 95 or 99.7. All I needed was 68. That's the only number I needed to use, and really 100%, but that's the only number from the empirical rule I needed to use in order to solve this problem. So you don't always need all three numbers. It depends on what values you're given. All right. I have a couple more examples here, and it's using the same situation. I just have it reprinted here because it was a while ago, so I just wanted to have it here one more time. And if you want to give this a shot yourself on these two problems, go ahead, pause the video, see how you do, and then unpause and check your answers. All right, so same mean, same standard deviation, and I have the empirical rule listed here yet again. What is the probability that x is more than 205? Okay, well, that's a number we haven't indicated yet. So I need to find where that is. Well, 205 is above 160 mathematically. So I'm going to need to go up standard deviations until I get to 205. If I go up 15, I get to 175. So not there yet. If I go up 15 again, I get to 190. So not there yet. But if I go up 15 one more time, I get to 205. So that's the number I was looking for. That means I want this small region here, that small little tail. Okay, so that's the area that we're trying to find. Yet again, that's not going to be a direct application of the empirical rule, but we can use one of the numbers from it. 205 is 3 standard deviations above the mean, and that's the only number I have. That means the only number I need to work with is 99.7%. That's the only number I need to work with, the third value in the empirical rule, because that represents how much area is within 3 standard deviations. Like the previous problem, though, it's not just going to be an answer of 99.7. We know that if we go 3 standard deviations away in both directions, which would be 115 to 205, this region here in the middle, this represents 99.7%. But we want the area in this tail. Like the previous problem, I can take 100% or the entire curve, subtract away 99.7%, and we get an answer of 0.3% in these two tails. So this left tail here and the right tail. Well, like the previous problem, if I just want one of these, I need to cut this in half because the data is symmetric, and we get 0.15%. So the probability that x is more than 205 is 0.15%. Or as a decimal, just to remind you how small this really is, that as a decimal would be 0.0015. So a very, very small amount. All right, so yeah, this tail would be 0.15%, and likewise, this tail would be 0.15%. You may even start to notice in some of these problems, as you work with the empirical rule more and more, you may not just memorize 99.7, you may also start remembering the area of the tails, because we do use those a lot. All right, hopefully you did pretty well on that one. This last one, number 5, this one's a little bit tricky. X is between 145 and 190. All right, thankfully, we've indicated where each of those are before. We know 145 is 1 standard deviation away from the mean. And then 190 was 2 standard deviations away. So if I go up 15, and then if I go up 15 again, that gets me to 190. So I want the area from there down to there. All right, there's a little bit of a weird thing here. 145 is 1 standard deviation down, so minus sigma. Whereas 190 is plus 2 sigma. It's 2 standard deviations above. That means we need to use 2 different numbers. There are a couple different ways of applying this problem. I'll do one way and then I'll talk about the other one. All right. The way that a lot of people work with this is keeping in mind that the data is symmetric. So what that means is if we cut this in half, we should be able to find the data in each of those pieces. If I look at the area here, from 145 to 160, that's 1 standard deviation, but I only want half of that. So this area is going to be 68 divided by 2, which we did in part 3. Comparatively, the area here, from 160 to 190, that's 2 standard deviations, but I only want half of that because I don't go down to 130 like I did in part 1. I only want half of this, so this is going to be 95 cut in half. So all we need to do is take 68 divided by 2 and add that to whatever 95 divided by 2 is. 68 divided by 2 is 34. We answered that in a previous problem. 95 divided by 2 is 47.5. And then that together adds up to 81.5. So we have that the probability between 145 and 190 is an answer of 81.5%. That's probably most individuals' solutions for this. There are other alternatives. For example, we noted before that from 145 down, this was 16%. And we can also find the area from 190 up by doing our previous process from 3 and 4. And we'd find that this is 2.5%. So you could comparatively also do 100, take away the two tails that you don't want. So take away 16 and 2.5, and you will get the same solution. So there are multiple ways of approaching that problem. Okay, those are two of the most common ways. There is a third and a fourth way. There are a lot of different methods, but those are probably the most basic ones, and particularly the first way. Okay. Now we're not going to end there because the empirical rule, as you noticed, there is a lot going on here, so I want to do a couple more examples of them, but I want to approach them in a little bit of a different way. The serum cholesterol levels of a population of 12 to 14-year-olds follow a normal distribution with a mean of 162 milligrams per deciliter and a standard deviation of 28. What percentage of the 12 to 14-year-olds have serum cholesterol levels between 134 and 190? So this one's a little bit different because it applies actual context to the problem. You can apply context to all these different situations, and it's not that hard to do so. The difficulty there, though, is that it becomes more of a word problem, and students do have problems with that. Just try to break it down into all the necessary information. We know it's a normal distribution. We have a mean of 162 and a standard deviation of 28. So I'm going to write those over here. Mean of 162 and a standard deviation of 28. What percentage, so that means we're trying to find area, what percentage of the 12 to 14-year-olds have serum cholesterol levels between 134 and 190? So those are going to be my x values, the values that I put on the x-axis. All right, so that's all the information I need. So I'll say maybe like x1 is 134 and x2 is 190. Those are all the values that I need, and now I don't really need to look at the situation anymore. Now I could just take these values, draw them in a graph, and figure that out. All right. Well, I need to find out where these values are relative to the mean. So first, 134. I know that's below the mean somewhere, so let's start going down standard deviations until we get there. If I go down a standard deviation of 28, that means I get to 162 minus 28 gives me 134. Nice. So I'm already done there. One standard deviation down. Now let's see where 190 is. 190 is above 162, and likewise, if I go up 28, I get to a value of 190. And what I'm trying to find is the area between those. Probability that their cholesterol level is between those two values. Well, that's nice. That's one standard deviation up and one standard deviation down. So that means that the probability that it's between 134, again, you don't need to write this. I just like to write this because probability speak. Between 134 and 190 is just 68% via the empirical rule. I don't need to do any fancy maneuvering like I did in the previous problem. Just straightforward 68. Second situation is kind of similar. Still have the same mean and standard deviation, this one says a cholesterol level of 218 or more is considered dangerously high. Approximately what percentage have dangerously high level of cholesterol? So we just have the one number 218. So x of 218. And I need to find out where that is. Well, the center here is still 162. And 218 is somewhere above that. So let's start counting. If I go up one standard deviation, which is a value of 28, I get to 190. So not quite there. But if I go up another standard deviation, I get to 218. So that means I found that this value is 2 standard deviations above the mean. Furthermore, what we're trying to find is they have a dangerously high level of cholesterol, which is 218 or more. That or more tells me that I'm trying to shade this region here, this tail. We can solve this using the process we did in the last few questions. We can solve this by saying, all right, well, 2 standard deviations via the empirical rule, or 68, 95, 99.7. Via the empirical rule, I should only be needing 95, but I want the tail here. If I go 2 standard deviations up and down, this would represent 95% of the data. And I want this tail. So we should be able to take the full curve, which is 100%, subtract away 95% from the center, and we find that there's 5% in the two tails together. So this tail on the right and this tail on the left. Cut that in half, we get an answer of 2.5%. So the probability that x is greater than 218, I get is 2.5%. So that's what I'm looking for. 2.5% up there, and also 2.5% up there. We don't really need it, but it shows that the full curve is still 100%. All right. Hopefully you're noticing how important the empirical rule is, and also applying the simple concept of symmetry, that the left side is equal to the right side. All right, I have one more example here that has some more applicable circumstances, and then we'll end there and save the rest for the third video, or the third section. Example 4. In an English course, students turned in a final paper. The mean grade earned by the class was 76.4, the standard deviation of 3.2 points. The scores are approximately bell-shaped. Note, like in every situation, we have to have that. We have to know that it's normal or bell-shaped in order to apply this stuff. If it's not normal or bell-shaped, that standard deviation may not be important or relevant at all. Approximately 68% of the final paper scores were between what two values? So this is a little bit different. This is giving me the percentage first, and then asking for the x values in question. Well, if I write my empirical rule, 68, 95, 99.7%, if I'm asking for approximately 68%, that means I'm looking for one standard deviation away, where the mean is 76.4 and the standard deviation is 3.2. Well, on my graph, I have 76.4, and if I go down one standard deviation, 3.2, I get to 73.2, and if I go up one standard deviation of 3.2, I get to 79.6. Via the empirical rule, this should represent 68% of the data. So my answers are 73.2 and 79.6. So those are the two values I'm looking for. In this case, we're not looking for a percentage, we're looking for the two values that separate out that percentage. So just using the empirical rule in reverse. All right, the top 2.5% of students scored more than what value? So the top 2.5% scored more than one value. What value? So that means we want a region up here, not exactly sure where, but this area represents 2.5%. Well, if we apply the empirical rule, we can find this, particularly since we just did a question very similar to this. We found, if I scroll up to this question here, 95% of the data has 2.5% in each of those tails. So that means here, this 2.5% tail would have to have this 2.5% tail down here, and thus 95% in the middle. That means what I'm really looking for is this value, which is 2 standard deviations away from the mean. So 76.4, if I go up 3.2 once, and then up 3.2 again, I get to 76.4 plus 2 times 3.2, or 6.4. And we get an answer of 82.8. And that's the value I'm looking for. 82.8. That's it. Just trying to find what value would represent this percentage. Last one. A score of 70 is considered passing. What percentage of students passed this exam scored 70 or more? Okay. So this one's a little bit different because now we have a value given to us and we're trying to find a percentage. So 76.4, I want to see where 70 is in relation to that. 70 is below 76.4. If I go down 3.2, we get to 73.2. So not quite there yet. And if I go down another 3.2, I get down to 70 exactly. So that's where 70 is. Now careful here. It didn't say that we want the area of the tail this time. We want 70 or more. So that means we want this area here, which includes this right tail way on the side. Well, there's a couple ways of finding that. We know 70 is 2 standard deviations, and if I go 2 standard deviations away, black, change my, there we go. If I go 2 standard deviations away, this represents 95%. And we also know from the previous question that this tail is 2.5%, and this tail is 2.5%. So we can find this area in a couple different ways. We can find the probability being 70 or more by taking 95 plus 2.5 to give me 97.5. Basically just adding this middle region and the tail. Or I could have also solved this by taking 100, the entire curve, and subtracting away the one tail that I do not want on the left side. So taking away this tail. That will also give me 97.5. So a couple different ways to solve for the same question. Okay, that does it for empirical rule. There is a lot of examples there of applying the empirical rule. In almost every circumstance, it's about trying to find what value from the empirical rule do you need. You very seldom, if ever, will need all 3 numbers from the empirical rule. I think we had one example where I needed 2 of them. In most circumstances, you need just 1. Identify what number you need from the empirical rule. Draw the picture. That's very important. Draw the picture. And then use the picture to try to determine what percentage or x value you need to represent. However, with that said, that's everything that I want to talk about in this video. In the next video, we're going to be talking about z-scores, which is going to be how to find the probability when the numbers in question aren't exactly 1 or exactly 2 standard deviations away from the mean. What if they're somewhere in the middle? With that said, go ahead and try your hand at a good amount of the problems on the homework and the quiz until you get to something about z-scores, or if you see percentages that aren't familiar from the empirical rule. That should be everything, so I hope you have a nice day.